And I will introduce the first two speakers for the first presentation, which is Past, Present, and Future of Quantum Science and Engineering at Texas A&M. And let me introduce somebody who probably doesn't need much of an introduction for those of you who are in the field of quantum science, Marlon O'Scully. He's an international recognized pioneer in laser physics and quantum optics. Psst! That worked. He's holding appointments at Texas A&M University and at Princeton. He's also the director of the Institute for Quantum Science and Engineering at Texas A&M. He earned his PhD in physics from Yale University and had really a stellar career. His landmark work was on Scaly-Lamb quantum theory, was the first one to fully explain laser operations. He also built a lot of quantum optics groups around the country. There was an Optical Sciences Center at the University of Arizona, Center for Advanced Studies at the University of New Mexico, and then the one here at Texas A&M, the Institute for Quantum Science and Engineering. He really sort of shaped the field through experiments and theoretical breakthroughs, and I'm not going to go into any details, but let me also mention that he's been recognized with a lot of really good awards, like he's a member of the National Academy of Sciences, the American Academy of Arts and Sciences, Academia Europaea, and the Max Planck Society. And he has also received one of the highest honors in physics and optics, and including like the Humboldt Senior Faculty Prize. In addition, he has served as the Howard Loeb Lecturer, received an honorary doctorate from the University of Ulm in Germany, and was honored with the Herbert Walter Award. And then there's a second. Vandalie Bernardo. Is he speaking here? Are you the only speaker? Because I have a second. Is he the only speaker? Because I have Bernardo here as well. Okay, Vandalie Bernardo is here. He's the second speaker also in the same section. So I'm going to introduce him right away as well. So he's a distinguished physicist whose career bridges fundamental research, applied science, and science outreach. He earned his PhD in physics from MIT and currently serves as professor of biomedical engineering at Texas A&M University and as professor of physics at the University of Sao Paulo in Brazil. He's an elected member of the U.S. National Academy of Sciences, the National Academy of Engineering, the Brazilian Academy of Sciences, the World Academy of Sciences, and the Pontifical Academy of Sciences of the Vatican. His research really goes across optics, atomics, molecular physics, cold atoms, and biophotonics. He has made groundbreaking advances in photodynamics therapy for cancer treatment and many, many other things. Beyond his scientific contributions, he's also contributed quite a bit to education. He's very passionate about this. He has published instructional materials and even launched a dedicated television channel to bring science lectures and demonstrations to the Brazilian public. He has published hundreds and hundreds of papers. I stopped counting after a while, and has received many awards, including the Robert E. Hopkins Leadership Award, the Almirante Alvaro Alberto Award, Jose Rice Prize, and the Comendador da Ordem Nacional do Mérito Científico from the President of Brazil. So he really integrates education, innovation, and benefits of science. And with this, I'm going to hand it over to the two gentlemen to give us their first presentation.
So, good morning. Welcome to Texas Atomic and Molecular University. And it really is what we do these days, isn't it? So it's quite appropriate. I love Texas. I always had my heart here even before I got here. Was lecturing at Texas Tech as an invited lecturer back in the day when people were trying to understand gauge field theory. And I had the good pleasure of having a bunch of students. I'd come in once a week, got to electroweak unification. So I got there the first day and I said to the 30-odd kids, which Texas physicist got the Nobel Prize for electroweak unification? And they all looked at me. These were smart kids. I couldn't figure it. So I said, well, what's the matter with you guys? It's Steve Weinberg. They said, he's no Texan. But you're all Texans, and I'm proud to be here this morning. Thank you, Olga, for all your hard work, and Alexei. The notion of looking at what's going on across the state And here at the University, Texas A&M, it's a great idea. I especially would like to dedicate this lecture to David Lee, a Nobel Prize winner for proving the superfluidity at low temperatures of helium-3. The A&M activity in quantum optics is something which has a long-standing and which goes well beyond the Texas A&M College Station. It spans the spectrum into other universities and groups that we collaborate with around the state and around the nation. 3 Nobel Prize winners: David Lee, Dudley Hirschbach, great chemical physicist, and Roy Glauber. Glauber was here toward the end of his life. We're very pleased to have a great group of guys working on a variety of topics. The Scholar GPS looks at what we're going to be discussing here at Texas A&M, and by an algorithm that they put together, not us, they come up with Texas A&M as up high on the list with number 3, meaning something, but never mind. What's wrong with this picture? Here's what's wrong. As Professor Bagnotto and I will both gratefully acknowledge, this is where technology in the US of A got its start. And we're very proud of Massachusetts Institute of Technology. We don't even dislike Caltech. But we don't want to put ourselves ahead of Mother. So what we're working on here spans the spectrum from quantum optics applied to problems in general relativity to quantum optics applied to problems in biology, like scanning the surface of a coronavirus. The quantum eraser, which you may have heard of, looks at the erasing of information and the restoration of quantum coherence. And it is in a couple of papers, but most notably for the point of view of this discussion, Gottfried's book has it on the cover. Great guy, Kurt Gottfried, Cornell, Harvard physicist. Zuhail Zubari, who is here and is one of my very favorite colleagues, has an interesting story to tell about quantum communication in which he shows how to communicate information without really sending photons from Alice to Bob. And Yakir Aharonov said it right. He said, well, this is the closest that one could ever come to realizing Einstein's spooky action at a distance. Even made it to the Wall Street Journal. We are also very enthusiastic about and proud of our colleagues who are working on biophotonics using, for example, NV diamond, nitrogen vacancy diamond, and looking at ways in which one can probe the insides of cells and, well, cells primarily. Mikhail Lukin came up with a clever idea some years ago of putting these NV diamonds in a cell and then heating the cell preferentially at different points and measuring the time evolution of that temperature as things progressed. Quantum, as we all know, has 2 facets these days. Good old quantum mechanics from, say, 1925 to 99, something like that. But in the last couple of decades, entanglement and quantum involvement in problems like biology is taking center stage. Grish got the Breakthrough Prize for showing how to use squeezed light to improve images. Vlad has done fascinating work on quantum sensing at range, flying an airplane 10 miles up and looking at what's on the ground by backscattered Raman. The notion of looking at what's in the air from the ground or the other way around is something which has been a focus of our research here at A&M and at Princeton for a long time. Dick Miles and Arthur DeGario, Princeton A&M physicists, and I'm happy to say that I'm an A&M Princeton guy. I spent a decade there and enjoyed learning from them. So looking at ways in which you can, for example, probe a cloud by inverting the population in your mind's eye of a cloud and having it laze back at you. That's not exactly what we do, but it captures the spirit. Ping Yang is a excellent ocean optics guy. Is Ping here? I don't see him, but you should corner him and get him to tell you the story. Where's my timekeeper? I've got 3 minutes left? Good, thank you. Again, the application of quantum mechanics to biology is something which I think is a fantastic payoff. For example, back in the day when we were studying the detection of anthrax at Princeton, remember the anthrax-laced letters were mailed at a post office in Princeton. And we had a strong group there learning how to use coherent anti-Stokes Raman scattering to detect a particular molecule, dipicolinic acid, within the anthrax itself, 17% by weight. And that we were able to do, improving the detection time from, say, a minute. Here's a sample. What's in it? Is it anthrax? Well, we could tell in a minute just using Raman. And then using coherent Raman with femtosecond technology, we got to where we could, that is to say, Alexei and his group here, and our other friends, Arthur DeGario, Dick Miles, Vlad Yakovlev. I know I'm forgetting somebody, so straighten me out. The next application I'd like to point to is the application of quantum technology to detecting the amino acid molecules on the surface of a coronavirus. I'll say that again. A single molecule, amino acid molecule, so what are we? A few nanometers, a couple of nanometers. And you can scan the different molecules on the surface of the virus using coherent and supercoherent Raman. Olga got the Ramsey Prize for her work on X-ray nuclear optics, which Ju Yi told you about, and I hope you get a chance to talk to her about that. The dark matter as an application of quantum sensing, Rupert is really building state-of-the-art devices. Oh, sorry. So I'll just quickly mention our colleague Zond, who's making nano systems out of colloids in a chemical sense, and Anatoly Shvedzinski has shown something very interesting. We all know that if I have a cavity containing n photons, the cavity is in volume V, then modulo some factor alpha in a time t, you can look at the rate in which, or the ring down time, let's put it that way, of the n photons driving that single atom. That's well known, and garnered the Nobel Prize for Serge Haros a decade ago. But now we show that it's possible to have a cloud of N atoms with one photon and get essentially the same ring-down structure, the same equation, except that now this is the number of atoms, not photons, and this is the volume of the cloud. And I think I'm about done there. Forgive me, guys, for hurrying through stuff. Quantum thermodynamics, quantum heat engines are something that we'd like to, she says time's up. So I'll just tell you about Zuhail Zubari's a fantastic book here in which he teaches quantum mechanics to freshmen. And he does a real job of it. He doesn't give them some kind of watered down whatever. But I strongly recommend that, well, I hope you buy this book first. Little joke there. But this is an accomplishment that garnered him the highest prize that you can get as a professor. At the end of his lectures, at the end of the semester, these freshmen give him a standing ovation. So I'd like to give you all a standing ovation for being here and helping us really push the quantum in Texas. Thank you for your attention. Here's the guy who's a member of the National Academy of Sciences, the National Academy of Engineering, and everything else. Help me out.
Thank you.
He's going to talk more about the technology and the science, but mostly technology.
Okay, well, it's good morning to everybody. It's a pleasure, and it's a very hard task to divide the stage with Professor Marlon Scully. So we all know why we are here. We are here to make sure we have all the ingredients to make these quantum new devices to go on. And I'm going to try to explain less about the science, but I'm going to give a few examples of things I'm doing. And recently we have done a meeting at MIT with many of the leaders on this field, on the Vatican Academy of Science. And then I will point some of the concerns and some of the conclusions that was taken in that may help us to guide towards a few things. We all know that quantum is around for a long time. We are celebrating 100 years, but even a few decades before, people were thinking about. And there are so many devices that intrinsically has quantum effects on it, right? I mean, we cannot live without quantum science today. All the things you can see in the screen are devices, are components that has intrinsically on it, behind the scenes. Maybe you do not know, but any transistor has some quantum effect going on. GPS that we use it to even walk inside our house today, everything has quantum on it. You know, we saw some wonderful talks by clocks that, you know, it's going to increase a lot what we can do in many sense. And so there is no question that quantum is something already involved in technology. But behind the scenes, normally what we get out of there has classical concepts going on to observe. And of course, I cannot read all my transparency here behind, but quantum, we cannot question the importance of quantum. And it is important for economy. You know, there are reports around that's going to show you what is the contribution of those things that goes from laser to electronic components to machines to do NMR and everything, healthcare, everything. Even the car today has quantum components that you don't even know. So economy is there. And quantum is making good contribution for economy. What is different now? Well, what is different now is that quantum got out, is not anymore behind the scenes. It's on the scene. And we are dealing with the real quantum effect to defining new applications. So here I took it three, like quantum sensing, which is important, maybe even more important than quantum computation. We don't want to take, we depend on computation today. Better computers will be much better. But we cannot forget that all the time we are detecting, we are, based on detection, we are acting. And quantum detectors, quantum sensors may be wonderful, especially for Texas. With atomic interferometers, we can know how we are emptying the reservoir of oil or maybe water or everything else. So this is important. Of course, quantum communications, because this will increase the security and will increase the speed and everything. And quantum computer. Even though those are the pillars of those new applications, because they depend on real quantum effects that you observe. The quantum effects are not anymore behind the scenes, right? This is the difference. It is the same quantum science that we built up for 100 years. The only difference now is we have to know exactly how to deal with the peculiarities of quantum. As Michael said, show the guy like pass in both sides of the tree when they are skiing. That's the thing we are facing now to do the new technology. So, but it goes beyond, really quantum applications today goes beyond those pillars. Those are very good pillars, but it goes much beyond. We have atomic clocks, we see. That's fundamental. We have quantum simulators. We have applications in life science, climate, agriculture, and much more. And what is the unique things that we had in what they call the old revolution and the new revolution? We need the people that knows quantum. That's why everybody in this room is interested in showing what they are doing, to just demonstrate that our capability to keep going and advancing in this new area, which is the same quantum science. We didn't invent the quantum science again. It's the same one. But now, applications and understanding is a little different. I am afraid to give a quantum computer in the hands of an engineer that never had any background in quantum science. What are we going to do? It's different. It's not electron passing here and there, which is already very hard for some engineers to understand it. This is a different concept. Intuition has to be built up. This is a good concern we have to have. And, there are many examples that I could give you. And if we're going to do quantum technology the way we see, we're going to put things in the market. I think we should worry about this is a type of technology that has to be strongly connected to science all the time. Because if you're going to put a quantum computer, that will be the zero generation. This has to grow. It's always going to be connected with science. Again, that's why people are looking for quantum scientists to be part of this whole thing. I don't know a single quantum company that doesn't have a big, big body of scientists involved, right? And some of the people are here. Okay, so we have to know that. And then whatever we're going to go, we need to know that there is a lot of quantum scientists orbiting that place. Otherwise, we're going to be in no-land space. And of course, I'm not going to repeat what Professor Scully said. This is a place that's been orbiting with quantum science for a long time. And Texas in general is orbiting with quantum scientists. So we have the most important ingredient for actually jumping to the new technology. And this is a message that the governor has to have. Do we have the ingredients? Otherwise, we're going to start to prepare the meal, and we forgot the salt. 5 minutes, oh my God. Okay, I'm not going to speak about different examples, and I am involved in some quantum simulators. We have examples, and I'm doing that with both condensate, taking out of equilibrium, you know, and try to see how the system evolves in time. This is something that our computers cannot do it, or classical simulations cannot do it, or numerical simulations cannot understand how a system composed with many particles together will evolve in time. How they're going to build up the statistics on that and everything, and that we can simulate. And of course, I am in the biomedical engineering department, and I'm going to use quantum all the time in my work. And this is a new proposition that we can construct a different type of microscope that we actually will see correlation between sides, time or space correlation of photons that comes out. And with that, we can discover real quantum stuff going on inside the cells. But I just want to scan through the main conclusions that we took in this big meeting that we had in the Vatican Academy of Science. You should know that the Vatican Academy of Science is in Vatican, but we almost never pray in the meetings, okay? But we do discuss what's relevant for mankind. And if you see here in the picture, many of the people that are in audience and gave plenary speaks, they are here, you know, and we had people from IBM and for all the main players in this business. And Looking was here, Junior, Chris Monroe, that's going to be tomorrow, Scully, and many other people that I'm not going to spend all the time saying. And of course, you have to know that in that academy, maybe it's the only academy that composed by the main players of the formation of quantum mechanics. You know, Niels Bohr, Louis de Broglie, Schrödinger, Heisenberg were members of this academy. In fact, I have an old picture that I see Dirac sitting in the academy. I try always to sit there because maybe some important things will come by you to sit in the same chair, but it doesn't work that way, right? Anyway, lessons based on that meeting, there was a few days, what we learned. There are a lot of things we learned. You know, from the past, was not easy. Always there are the people against everything. And people did not believe in quantum mechanics from the very beginning. Important people did not believe. So that is something that is called determination and resilience that needs to be involved for us to overcome and go through. Well, basic research. How many money was invested to build up these 100 years of quantum mechanics? And this brings another message. If we're going to do quantum technology, it's nice to be, have some social responsibility involved with this whole thing. Well, there is a big impact. I can send you the report of this meeting. The status of the present, you know, we already demonstrated that we can do many things. Let's just prove it. And quantum technology is here, but there is a future to overcome, to go. But there are challenges, you know. We're not going to have a quantum computer tomorrow morning. And the question is, who is better prepared for that? And I think this is what Texas is looking for. Can we get prepared as soon as possible? Because there is no question that this will come. And there is no question that you need to be part of this. Now, future perspective, there are many challenges, you know. I think they were very simple in not saying what we need to do to reach the goal. But there are a lot of things, you know, he spoke a little bit about error and stuff, but there are a lot of things to come. There are industrial issues to overcome. The big players are involved, Google, IBM, and we are making a lot of startups. We needed to think how those startups are going to do it. They're not going to put product in the market. Startup in quantum technology is a little different from conventional startup. We need to think about that. We normally don't think, but we need to, because they need to be part of a big consortium. The big players already understood that. We need to understand now how to do it, right? To push our young kids to startups. And of course, we need always to worry a little bit about the impact of this in society. I mean, we are scientists. The only thing we keep in mind is social responsibility. We take a lot of money from the taxpayers, and we need to give things back. And then there is a list of things that came out from these things. And concerns, you know, there are a lot of concerns we needed to worry about, but global collaborations for solution folks seems to be, we already see Mike looking, he's in Japan, he's in Boston, he's in many other places, because you needed to put people together to find. Well, what is the message, taking home message? The technology is here. Don't try to be opposition. Try to be part of the solution. And there are a few challenges that we needed to overcome to really go and move fast. Thank you very much.